Today we will be talking about 6PE, IPv6 Provider Edge, or 6PE for short. It's a technology that uses MPLS for IPv4 to IPv6 transition. Why do we need 6PE? IPv6 is continuously evolving and its advantages become increasingly prominent, especially with the depletion of IPv4 addresses. However, it takes a long time for networks to evolve from IPv4 only to IPv6 only. In the early phase of IPv4 to IPv6 transition, IPv6 networks are not widely deployed, and IPv4 networks are still the mainstream. At this time, IPv6 islands, where local IPv6 networks are separated by IPv4 networks, may occur. The IPv4 plus MPLS solution is widely used on live networks. A key feature of this solution is that peers on the backbone networks do not need to maintain service routes. This lowers the consumption of CPU, memory, routing engine, and other resources on peers. On an IPv4 or MPLS backbone network, MPLS LSPs may have been established to carry VPN services. If such MPLS LSPs already exist, network administrators may want to use them to carry IPv6 services. This is where 6PE comes in. How is an 6PE tunnel established? Simply put, 6PE adds two MPLS labels to IPv6 packets. The inner label, L2, corresponds to the IPv6 prefix, and the outer label, L1, corresponds to the LSP between 6PE devices. The IPv6 packets can then be correctly forwarded to the destination across the IPv4 core network. The way in which 6PE works can be described from two aspects. On the control plane, 6PE allocates MPLS labels to IPv6 routes based on MPBGP, whereas on the forwarding plane, it forwards IPv6 packets based on outer MPLS labels. The 6PE tunnel processes packets on the PE1 and PE2, which are two border nodes. Other nodes, such as CE1, CE2, and the P, are unaware of the tunnel. Because IPv6 packets are transmitted between CE1 and PE1, and between the CE2 and PE2, and IPv4 packets are transmitted between PE1 and PE2, PE1 and PE2 must be able to process both IPv4 and IPv6 packets. In other words, IPv4 or IPv6 dual stack must be enabled on border routers between the IPv4 and IPv6 networks. Other nodes only need to maintain the IPv4 stack. PE1 and PE2 use MPBGP to advertise IPv6 routes. Core devices have only IPv4 routes and LFIBs and no IPv6 information. Next, let's look at the 6PE route transmission and the packet forwarding process. As shown in the figure, CE2 sends a route to CE1, and CE1 sends a packet to CE2. L1 indicates the outer label allocated by MPLS, and L2 indicates the inner label allocated by BGP. The 6PE route transmission process is as follows. Step 1. CE2 sends an intra-AS IPv6 route to PE2. Step 2. Upon receipt, PE2 changes the next hop of the route to itself, allocates an inner label to the route, and sends the labeled IPv6 route to its peer PE1. Step 3. Upon the receipt, PE1 recurses a route to a tunnel and delivers route information to its forwarding table. PE1 then changes the next hop of the route to itself, removes the route label, and sends the route to CE1 as common IPv6 route. This way, the route is sent from CE2 to CE1. So what about the 6PE packet forwarding process? Step 1. CE1 sends an IPv6 packet to PE1. Step 2. Upon receipt, PE1 searches its forwarding table based on the destination address of the packet, and then adds an inner label and an outer tunnel label to the packet. Step 3. PE1 sends the labeled IPv6 packet to the P through the public network tunnel. Step 4. Upon the receipt, the P swipes the outer label of the packet and then performs PHP to remove outer label L1. Step 5. After PE2 receives the packet, it removes the L2 label and forwards the IPv6 packet to CE2 based on destination address of the packet. 6PE has the following advantages. First, all configurations are performed on PEs, and IPv6 networks are unaware of IPv4 networks. Any existing IPv6 routing protocol can be used between PEs and CEs. In addition, 6PE can leverage existing MPLS network resources and IPv4 networks to carry IPv6 services. It can provide IPv6 services without requiring network upgrade or reconstruction. It can even use TE to ensure service forwarding. 6PE devices can provide both IPv6 and IPv4 VPN services. Currently, 6PE is still used for Internet services provided over the public network. However, 6PE is equivalent to placing all IPv6 networks connected through 6PE in one VPN. It cannot provide logical isolation. To logically isolate the connected IPv6 networks, that is, to implement IPv6 VPN, 6VPE is introduced. We will talk about 6VPE in the next video. MPLS-based 6PE allows ISPs to connect IPv6 networks over existing IPv4 or MPLS networks by simply upgrading PEs. For ISPs, MPLS-based 6PE is an efficient solution for IPv6 transition. However, 6PE depends on MPLS and its protocol states are complex, failing to meet SDN management and control requirements. PEs need to support IPv4, IPv6 dual stack, which consumes more CPU and memory resources. As IPv6 networks become more and more popular, carrier network will one day fully support IPv6 and be able to directly communicate with each other through IPv6. At that time, 6PE will no longer be required. The ideal situation is that PEs only need to support the IPv6 stack. This lowers requirements on PEs and consume less PE resources. 6PE will disappear once IPv6 becomes prevalent on backbone networks. However, transition technologies such as 4PE that use the IPv6 backbone network to connect IPv4 island may emerge in the future. It's difficult to say what will eventually happen. Although IPv6-only communication is simple, it lacks SLA assurance for traffic forwarding. So how can we guarantee IPv6 packet forwarding on the backbone network? This is where SRv6 comes in. Briefly, the core idea of SRv6 is to divide an IPv6 packet forwarding path into different segments and insert segment information into packets at the ingress of the path to get packet forwarding. It uses a source routing mechanism to implement path planning and TE. SRv6 provides better network programmability and more flexible path planning, and it's the future of IP networks. That's all for today's video. Thank you so much for watching.